Swayam Prabha. Digital India. Educated India.
For today, I want to show you some examples of Fokker-Planck equation. So which would be also some simulation example. I will do some simulation just on as a demonstration for you, and. This is about Fokker-Planck. So we have original equation, the same as the in previous time. This is the system is composed of a beam with piezoelectric, and the excitation is stochastic. It is like a stochastic force. And I already mentioned you about the linear system. So this was linear. The top one example without a coil, and this is only piezoelectric and mechanical structure. And for this system, we already estimated what is the output, power output. So let me remind you, we have done some. So this is the analysis with an assumption that you have here the linear restore force. So there is a linear restore force, and if it is linear restore force, every terms are linear. There is also a stochastic term force on the right hand side of the first equation. And this is in fact the force which could be estimated for the transform, because if you have some Gaussian distribution, then a transform like a Fourier transform or Laplace transform is giving you the constant, and this constant would be here related with some, masses, and this is the dimension. So you can go also to non-dimensional equation, and this is done in this in the lower equation. There is a equation which is decoupled. So you have first order derivative only, and the z vector has a meaning that there is a displacement as a first element. There is also velocity and voltage. Yeah. So in the upper two equations you have x double dot. So this was decoupled to two equations, and the first order, and the second equation is for voltage v. So this is like a single equation. So you have three variables, and these variables are just included in the vector notation. And when you have such coefficients which were in the original form. So you have a matrix equation. So matrix there is still mass in the capital B. So this is still a dimension equation. So this is the form of dimension equation. And I think maybe for this part we will keep the dimension equation, because this is a linearized system, and finally there is S0 is a strength of random process. So you see that random process, this Gaussian random process, is characterized by the autocorrelation function, and this autocorrelation function is for uncorrelated noise. So you have only correlation if you have the same time events. So this is delta, Dirac delta on the right hand side, and if you now imagine that you want to calculate the Fourier transform or Laplace transform, then it would be constant, because this is by definition it's a constant value if you calculate transform for the Dirac delta. And now, if you moved from the this is the domain, it's different domain. So you moved from time domain to frequency domain. When you need to observe what is the what is needs to observe how to solve these equations. You have still linear, but if you look for x and b, there is some inverse. So you have also determinant of the matrix delta. It's written delta. I am telling you about this manipulation with a Fourier transform, and the drawback of this manipulation is that you obtain also some imaginary numbers. So the imaginary numbers are coming as I times omega, and if you have a second order derivative, then this is I times omega to square, and when it is easier because this is already a real part. However, if you have such a formulation, you can see that. So I already discussed this for the linear system, but for some reasons I was thinking that this is also important for the nonlinear systems, because in our Fokker-Planck equation, we want to decouple the equations to the mechanical part and electrical part, and this is the in such way we have the standard deviation or variance. This is sigma is standard deviation. Sigma square is a variance of voltage. So if we have some distribution of voltage, then you calculate variance, and the variance is also appearing in the power. So here there is still some problem, but there is missing square here. So the missing square is here. So this is the output power. If you take the average, you have the standard deviation, which is squared, divided by R, and you have a formula which is like a linear from the linear system. This is which was obtained from the manipulation by Fourier transform. So we moved to the frequency domain, and I am telling, but it is also possible to get this variance in some other way without using transformation, Fourier transformation. So this is the good result, and if you look to this figure, which was published by us in 2013, you can see that the variance. This is actually variance of a voltage output, which is proportional to power, can be estimated in such way. In this system, however, we did some linearization. Yeah, so this is additional point to the Fokker-Planck, which I would start in a minute. However, in this linearization, we used the linearization is that we have some noise, which is relatively weak noise, and we can manipulate also with a level of noise. The level of noise is given by the variance of the stochastic force. So this is known, and in the previous transparency, you can see that S0 is a level of noise. S0 is level of noise, and the power is proportional to this level of noise. So this is the estimation of variance for the linear system, and if you have linearized formula, you think that the force is linear, so the potential should be selected in such way for the linear system that you have a parabol which is fit to the potential, and from the coefficient, which is like a parabolic coefficient, you can predict what is the linear contribution. And of course, there is a shift if you look for the double well potential, which is on the left-hand side, the upper panel. You can see that there are two potential wells. However, this is not so bad, because these two potential wells are equal and they have the same coefficient. If you fit the parabol just in the inside this curvature, you can estimate the coefficient, the linear coefficient for our system. And if you go to higher, this is alpha is the original parameter, the linear part. If you have two parts of the polynomial for the potential, you have a square term and fourth order term, and alpha is original coefficient, which is coming to the square term, and in the beginning you see that this is negative. So on the horizontal axis you see that alpha is starting from negative value. So if a negative value is spheric, you can expect that this is double well. But if alpha is 0, then this is so-called quasi-zero stiffness. Quasi-zero stiffness, and if alpha is positive, you have a single potential well. So in this case, we obtained that power is the largest just before we obtain the quasi-zero stiffness. Quasi-zero stiffness is without it's only single potential well, but with some flat effect in the equilibrium. So equilibrium is very flat here, and there was some question on the previous session, which barrier is most useful for the system. So from this calculation, you can tell that this small barrier is the most convenient, because you can have still large amplitude of oscillation, but the energy which is in the system needn't to be very large to overcome the potential barrier. Yeah, so this is also consistent. This result is also consistent with such a statement that you have two effects. One is enlarging the amplitude of oscillation, because the potential is for the mechanical system, and you can expect that if you have two potential wells, you have larger distance between the equilibria. this could be larger response in amplitude. However, you should remember that if you produce such a barrier, then you need stronger excitation. Yeah, so this is like a competing of these two effects. So you have some compromise between the height of the potential barrier and the width of the minima, which is here. Yeah, between the equilibria minima, the stable equilibria are in the minima. So it was obtained in such way. However, there is some theory about transformation, and this is coming also from this Fokker-Planck equation. So the transformation from the random equation, differential equation, to partial differential equations, which is not random. So then the next transparency, I just want to. This is still the linearization effect. You can see that. Yeah. Sigma 3, yeah, because I had such a notation but this is you know, the vector notation. In vector notation, sigma 3 was for the third component. So you have z is like a vector of a state in our system. So state vector, and then the first is displacement, the second is velocity, the third one is v. So v is voltage. Yeah. So the third component is voltage. So this is
variance in the sigma 3 is equal. So
yeah, this is equal because I discussed the results from two papers, and in one paper it is called just sigma v, and in the second paper it's like sigma 3. Yeah, so this is it is sometimes difficult to keep the unique notation. Yeah, so this is like a change of a notation. Yeah. So this is because there are two papers. So the first paper was in the dimension system. So you see all the coefficients, original coefficients like mass, capacity CP, and resistivity R I, and you have also you have also C, small c is like a damping coefficient. So all these components are here. However, in the next paper, we analyzed in a dimensionless system, and when we transferred to the new variable, so this is still proportional to it is probably still voltage. However, it is in dimensionless system. So maybe this is why it was used symbol sigma 3. Yeah. So here you have a procedure, but you look for the potential and you feed parabol. But the parabol can be fit in such way that you just look for the equilibrium point, and you try to find some coefficient for this parabol, yeah, which could the first on the left hand side you have already minimum, so there's like a single potential well, so this is quite easy, and you see that if you look for the force is not linear, because if you follow the full line, it would be some hardening, maybe hardening in this case. But if you see there is in the just at the vicinity to the equilibrium, it is a good fit. Yeah, it's a good fit. And the same can be done for the equilibrium, which are minima of the double well potential, and you have to fit some tangent line. The tangent line is it would be would give you the coefficient which is for parabol of the potential. So you have to choose, and we called this alpha star. So in the top of the figure you have we have written alpha star plus alpha star x plus c. Yeah, so this is the approximation at the vicinity of the restore force at the vicinity of the equilibrium point, and we have used such linearization to get this diagram for the variance of voltage. In this case, it's variance of voltage, and however, this is only part of story because now I would like to show you how to look for the new equation, which is not it's not stochastic but deterministic, and this is the Fokker-Planck equation. And Fokker-Planck equation it is deterministic, but it is a partial equation. And the object is also changing because here it is the original equation, but it is rewritten in some way. So you have maybe, because this is from other papers, so coefficients are slightly different, but this is the same system. So the notation is different. And you know from this part you can see that this is called Ito equation. And this is written in such a form of Ito equation, and when you from this equation you estimate state vector, and the state vector is like in previous time in the linear equation. This is like the first component, the first element is displacement, the second is velocity, the third is voltage, and when we have also some we have also some force which is coming here, like restore force. This restore force this is called F, but it is not actually restore force. The restore force is the middle element, is like a second element is restore force, but the first element is like velocity, because we decoupled the equation into two equations. So the derivation of velocity is the second element, and of this vector or this vector equation. So it is, and also with the same level, there is also noise, because noise is like a force. So force is coming to the second element, where you have derivation of derivative of velocity. The second element in x is velocity. The second element in small f is the force, restore force, and mechanical force, and the g is giving you sigma f is a variance of force. This is not variance; it's standard deviation of the force. Standard deviation of the force. And the force is constant, so it's random. So I mean this standard deviation is some constant. So standard deviation of the force is a constant. We have Gaussian white noise, and the integration is a little bit different, because you see that. On the left hand side you have dx, and on the right hand side you have dt and dw. And dw is the random noise. So the random noise is scaled in different way, and this is just to manifest that this term is a little bit different from the deterministic equation. Yeah, so how to do the simulations in the of a random system? It is also a good question, but you have some algorithms also in MATLAB and Mathematica, which are embedded. The noise is embedded, and you can make some simulations also in such way. But this is a random equations. This is random equation. For example, we need to remember what is the time step to the noise, because you can imagine that the noise would be scaled with a time step. If you have a small time step, then you can see that there is some effect, some accumulated effect of a random force, and this random force effect is changing with the square root of the time. It's not like delta t, which is coming for the deterministic system, but it is scaled differently. But I think that we can also analyze this. One example we can provide you for the next this tutorial with computing. So there would be such a tutorial, but I think maybe one random system can be also provided. How to do the simulation for random equation like that. So this is not very difficult. However, one should be careful because if you have variable time step, you need to change also this effect of noise. So this is where this could be a problem sometimes. Yeah. And this is the transformation to the probability. You transform from the state from the variable states variable to the probability distribution function. So the small p is probability distribution function, and this is called a Fokker-Planck equation. And you can directly transform provided that you know these coefficients, and these coefficients are small f and the bij and small f. And if you go to the previous part, you can see that this small f is given in this vector exactly. It is given exactly in the vector, and the b is related to this matrix G. Yeah, so this is square of G. Yeah, so it was maybe written in the next page. So the b, you see that the b in the bottom, it is written that b is a square of G. So in fact, G is very simple. So this is possessing only one element, and you would have also such a simple form of a B. This would be only one element, which is B22 would be non-zero. B11 would be 0, and the rest of B elements would be 0. Yeah, so this is such a simple case of noise, but we have noise represented as a force. So this is like a random force is present in the system. And then if we have such a formulation, then the problem is how to solve this equation. And I think this is the equation, partial differential equation. And there are many methods to solve a partial differential equation, and one of the method is solving like a finite difference. So the second could be finite elements. It is so I have here one paper by it is like old paper from 2000 2013 where in this paper such system was solved with finite elements by some researchers from Chennai and in cooperation with Professor Friswell, who was our also strong collaborator. He was strong collaborator also to me and to Professor Sheikh Farouk So I think finite element can be also applied here, but instead of a stress distribution and stress and strain distribution, you have here the probability distribution in some continuous volume. So this is some possibility, and then there are some even more different approaches because the field is still developing. Especially we have such we have such computational methods, and where computing time is smaller for new developments of computers. So I think some new methods are coming to that area, and you probably can find some other solutions. And I was looking for some solutions which could be demonstrated for you. But if we stick with this with this system, I mean that we can also I can also show you the original solution for the probability distribution function. I told you that there is some decoupling of the electrical part and there is a mechanical part. So if you calculate what is the probability density function in terms of x1 and x2, so this is x3. However, this could be also done. So you can have you can have such a probability distribution function, and in fact you can use some software which is available in the internet, and I found some software which was in the repository. This is a published paper in Springer book in some computational methods of stochastic dynamics, and the title was Numerical Solution of Fokker-Planck Equation by Finite Difference and Finite Element Methods. So you see that these two methods are probably just the best for solving these equations. And let me show you the software. Yeah, so I downloaded the software. So this is the link to download the software here. And I included, you see that this is called Duffing oscillator. It's a Duffing oscillator which I included, and there is some procedure how to use these parameters because this x1 x1 and x2 are just telling you what is f1 and f2, and the d is related to the 1 1 and 1 2 coefficient of this is the diffusion term with variance. So I think if you look to these numbers, then you need to just to find how many coefficients, how many terms you have in the in each of the F, like a drag force in our case. And for example, here it is velocity. It is written velocity. So velocity is it's a second variable, and the coefficient in front of this variable is 1. So there is 0 means that this is not the x1, but it is x2. Yeah. So the x2 is written 1 here, and here you have the force components, and where for force components you have restore force components, and then you have x to the power 1. So this is the first term, which is represented by 3 numbers. 1 means this is like a coefficient 1, and the second one means that this is like there is a first variable, and 0 that there is no second variable. And for example, if you have here -1 0 1 is that you have some damping. There is a damping coefficient is 1. Yeah, so it should be maybe smaller. We can put 0.1. Now this is coefficient, yeah, and when it's 0 and 1 means that this is velocity, and the third one is like a higher order term, nonlinear term, which is with -1. So this is in front of a term is -1 with this is negative term, and 3 means that this is to the power 3. X to the power 3. So this is such numbers. Such numbers. So we can have also some other which could be important for the double well with this is double well. Yeah, so the double well is here. Yeah, sorry. So double well is I'm not sure, asymmetric, but this is called asymmetric. So I mean the symmetric double well. We start from the symmetric double well. So I can just start with this simulation. So this is fine. Yeah, so this is comment, and I can start here with symmetric. Asymmetric double well. So I put here comment. Just want to make this is commented. It's now commented. So the green is commented. Yeah. So only this double well tapping is working. So you run this system. This is commented. So once again, it's pretty fast, and you can also show what is the result in terms of of the probability density function, and then this is not very big. Yeah, so you need to change height. So maybe even some values should include the range. So -10. I was thinking, so previously I had some different results which I tested with one here. Here one maybe it's better. So this is now it is coming the result which I expected. There is such a double well form and double peak with a probability. So when this is 0.5. So this probability distribution function is given like that. So you see that it is possible to do such a simulation, and there is some small description of that software on the web page which I provided. However, if you make some now I can do some change. But for example, we have a double well oscillator, but this double well oscillator is non-symmetric double well oscillator. So I have another example, and I can make this such way. So now this is going to work. I would tell that there are some other examples like van der Pol oscillator. Van der Pol oscillator is also present here, and there is some diffusion, but it was given by the authors of the software. So there is also some diffusion example, and for that you can estimate now the non-symmetric potential. I added some more term to the force, to restore force, but this is not only even but also odd term, like this is not only odd but also even term, like x to the power 2, but it is providing after integration, it could provide to the potential some non-symmetric effect. If I go now to the result, just a figure to be plotted, so you can see that this is the result would be non-symmetric. But what the authors provided, I think the calculations are going in some updating loops. So there are many loops, and each loop can be you can observe the convergence, and you can also make a short movie from this software, just looking what was the update to the original guess. So I just want to execute such a movie. It's a movie schedule. So I can show you the last example. like a movie. Yeah, so a movie. This is a calculation of a probability density function, which was presented on the last figure. But you can also move in such way. So this was the figure was. If you want to see the final distribution, this is given like that. But you can observe also how it was built after some number of iterations. So I think this was about the methods. So I presented you these methods by discussing the Fokker-Planck equation, how it is more or less how to derive this equation. So there is no formal derivation because it is more difficult, but I identified terms which are important in the Fokker-Planck equation. So you need to find such terms in the original equation, and it is possible to apply Fokker-Planck equation to different mechanical systems, but most of them are just these systems are just simple, like low dimensionality of a system. So in terms of a low number of variables. So we have two variables would be the best. We can use also three variables because I should tell that the probability the distribution function of our in our paper, which is the paper from 2013, which I reported, results reported. Yeah, so we estimated variance of voltage from the linearization. And then if you have a variance of voltage estimated from the linearization, you can plot the such a probability density function in terms of different variables x1, x2, and x3, because the representation of x3 would be very simple. So it is similar to velocity. It is oscillating around zero and with some estimated already variance. So it could be that just one of variable can be just removed, and this is the system with this presentation is with I think that I can rotate maybe this figure, but you have velocity and displacement. So this is like displacement. Maybe this is wrong description. So this is like it should be displacement and velocity. I'm not sure why it is reversed. However, this is simple, but it was written maybe in wrongly in this description of the figure. And if I repeat this figure, when this is now it is correct. So there is a displacement and velocity, and here you have probability distribution function. It is possible to avoid like here. This is possible to avoid some variables. So you can plot the cross section for given velocity and for given displacement, and also you can you see that there is no voltage here. Yeah. So some representations with a smaller number of variables can be also provided for the probability density function, and this is called marginal probability density function. So I would like to to stop with my presentation now. So thank you very much for your attention. So maybe there are some questions. Yeah. This is quite difficult topic, this poker plank, and we were working on this topic like 12 years ago, and recently in 2021 we renewed some results, and then we provided some other algorithm for calculation. So this is from time to time we are going back, because I would advise you to check some problems could be solved, but after a few years it could be that you can provide better solution to the same problem. Yeah, so sometimes it's worth to continue some topic and make some corrections. However, I don't advise you to just to limit to one topic for your research or your work, because it is good to have broad interest. It's better to have broad interest, and then it's easier to make any improvement. Yeah, if you focus too much on one topic, then this would be not such a good progress with research. Yeah. So thank you very much for your